Hi, Jerry.
I was hoping they'd do the vaccines in California alphabetically by first name, but that's not the order they're using. So.
Did you suggest that?
I should have written to the governor every day for the last year, but I haven't.
Well, he's pretty near the beginning of the alphabet with alphabetical by first name, so he might have gone along with you.
Well, it is 4 o'clock, so I don't want to take any time away from Allan. And so I thought I would go ahead and get started. And let me just briefly introduce Allan. I think most everybody on this chat probably knows AllanRossman, who's a professor of statistics at Cal Poly San Luis Obispo. And Allan has been teaching statistics for more than 30 years. I had the very good fortune of being able to work closely with Allan my last year as chief reader of AP Statistics, when Allan was preparing to follow me as the fabulous chief reader. And so I can't tell you what a great experience that was, and how fortunate we are to have Allan in the stat ed community. Allan also is program chair for the US COTS, which is coming up this year. So make sure that you think about US COTS later on. And what Allan is here to talk with us today about is his weekly blog that he writes, which is Ask Good Questions. And so I could go on talking about Allan, but like I said, I don't want to take time away. So Allan, I'm going to turn it over to you.
All right, thanks very much. Let me share my screen. Thanks for the kind introduction. Thanks for the invitation. Thanks to everyone for being here. So yeah, the title of this presentation is Ask Good Questions. And I'm going to start just like most statistics teaching.
Allan, we can see your next slides and on there. I don't know if you intend
That's
that.
too bad. That's too bad. Let me start over. Thank you. I must have picked the wrong screen to share. Let's try this again.
There you go.
Is that better?
Yeah.
All right, thanks. I gave away the first punchline then. I was going to say that this talk will start as most statistics talks start by showing a picture of Frank Sinatra. Let me get my buttons to work here. So what's Frank Sinatra have to do with anything? Well, legend has it that Frank Sinatra was once asked, what's the secret to being a successful singer? And legend has it that his answer was, sing good songs. My suggestion for being an effective teacher of statistics is equally succinct. Ask good questions. And I'm tempted to put up a slide that says the end. That's what I have to say. That's my take-home message. I'm going to have a quiz at the end of this talk, and I'll tell you right now, the answer is ask good questions. If you ever hear my name in the future, or maybe bump into me when we're out and about in society again, I hope that you'll immediately think, ask good questions. But I am going to talk for another 25 minutes or so and give you some examples of what I hope you'll consider to be good questions. What kind of questions do I have in mind with this slogan of mine? Well, two kinds. One is the kind of questions you ask every day in class to guide students' learning, to help them develop their understanding and their skills. You can think of those questions as formative assessment or as learning activities. And I also have in mind questions that assess what students have learned, which you can think of as summative assessment, quiz questions, exam questions, things like that. So as I say, I'm going to give 4 examples today. One is a very far below average joke. Another is about comparing cats and people. I'm a big lover of cats. Another one is what I sometimes call a pervasive pet peeve, which has really become a pet peeve of mine. And to be honest, I probably go way overboard in talking about this with my students now. But it deals with percentage differences and relative risk. And then the final example will be a probability problem that I really enjoy and use a lot. I call it random rendezvous. It deals not only with probability, but with simulation and geometry and algebra. The part of my theme with choosing these examples is that I think that the advice to ask good questions applies throughout a mathematics curriculum as well as to teaching statistics. So let's start with my below average joke, and here it is. I think when I moved from Pennsylvania to California 20 years ago, that the average IQ dropped in both states. After I tell that to my students, I have to wait a few minutes for the laughter to subside, of course, but then we get to the point, which is that possible, at least in principle? And if so, what would have to be true for this to happen? And I think this gets at, do students understand how averages work? Not just can they plug into a formula, but that they sort of understand properties and behavior of averages. I hope they realize, at least in principle, this could happen. The way it could happen is if I was above average in Pennsylvania, so when I left, the average dropped. And of course, needless to say, I'm below average in California, so when I entered the state, the average dropped. There's an example of a below average joke and perhaps a below average question. I think it gets at some kind of understanding about how averages work. Let me transition to talking about cats. Here's a question I like to use a lot. I often use this on final exams. And part A is very straightforward. My students do great on part A, which would be larger, the mean weight of 10 randomly selected people, or the mean weight of 1,000 randomly selected cats. If there's any trick here, it's that you have to realize that averages or means take sample size into account. So it doesn't matter that it's 1,000 cats. That doesn't make the cat's number bigger. People tend to weigh more than cats. So the answer, of course, is people. And as I say, my students do great on question A. Hardly anyone ever misses question A. Question B, my students do poorly on, which would be larger, the standard deviation of the weights of 1,000 randomly selected people, or the standard deviation of the weights of 10 randomly selected cats. So think about your answer. I won't put you on the spot and call on anyone. And I'll tell you, my students do poorly on this question, as I said before. Many of my students answer the cats would have the, which way did I say it? Larger. They say the cats would have the larger standard deviation. And that's not true at all. Think about human beings and their weights. Weights of human beings vary a lot. Even if you only consider adults, weights vary from 100 pounds to several hundred pounds. If you consider kids, you have smaller weights than that. Whereas if you take ordinary domestic house cats, the weights vary from maybe 5 or 6 pounds up to 20 or 25 pounds. So there's clearly a lot more variability in weights of people than in weights of cats. So the standard deviation will be larger for the weights of people than for the weights of cats. Why do my students, some of them, get this wrong? I think that they're thinking that a bigger sample size means a smaller standard deviation. And they'll probably tell you that they heard me say that in class. I promise you I did not say that in class. I said something like the standard deviation of a sample mean gets smaller as the sample size gets bigger. The standard deviation of a sample proportion gets smaller as the sample size gets bigger. But this isn't asking about the standard deviation of a statistic. It's asking about the standard deviation of the weights. The answer is people's weights vary a lot more than cats' weights. So my advice to myself and to other teachers is, whenever you talk about a standard deviation, always be clear to say standard deviation of what? Because students might think you're talking about the standard deviation of a statistic, and you're really not. Just for fun, here's pictures of my cats. Eponine on the left, Cosette on the top, Hootie, who's the current cat we have, on the bottom. That's 2 of my 4 examples already. The next 2 are a bit longer and they'll take a little bit longer. Example 3 is about a study that's kind of old now. It's 15 years old or so. It was about an attempt to help smokers to quit smoking. Smokers who wanted to quit were randomly assigned to one of 2 groups. One group received a nicotine lozenge, and it turned out almost 18% of the subjects in that group successfully abstained for an entire year from smoking. The other group was randomly assigned to receive a placebo lozenge, and a substantially smaller percentage of them successfully quit. Here's the question I pose to students. If we take the difference in these percentages, we get 8.3%. Is it fair to say the nicotine group success rate was 8.3% higher than the placebo group's success rate? And the answer is no, that's not how percentage differences work. That's the difference in percentage points, but that's not the percentage difference. And as I say, this is a pet peeve of mine, and it's pretty much become an obsession of mine. Every class I teach, whether it's appropriate or not, I spend some time talking about this. Let's think this through. How do you calculate a percentage difference? You take the actual difference and divide by the baseline value, and then multiply by 100% to make it a percentage. So let's do that with these percentages who successfully quit smoking. And just a question for you. I'm curious as to when students learn that. It's something they learn in, I have no idea when students learn that. When do students learn that? Elementary school. Like I said, I make a big deal of it in every class I teach. This year, I'm teaching a 2-quarter sequence for introductory business majors. I made a big deal of it in the first term, and I just last week made a big deal of it in the second term. So let's compare the nicotine lozenge versus the placebo. That turns out to be an 86.5% difference. The success rate in the nicotine group was 86.5% larger than the success rate in the placebo group. So if we use that in a sentence, I think that's probably the sentence I just said, pretty much. I always encourage students to look at that and ask, does that feel about right? Does it seem about right? I hope they'll realize that doubling means a 100% change. And 18% is almost double, 9.6%. So that seems about right. Let me go one step further with this. Like I said, it's become an obsession of mine. Another question I like to ask students in this context is, how many times greater is the nicotine lozenge's success rate than the placebo's success rate? How many times greater? Times is the key word there. We need the ratio to answer this. There's the ratio, 1.865. And we use that number in a sentence. Sure, smokers who receive the nicotine lozenge are 1.865 times more likely to quit than those who receive the placebo. And that number, by the way, is called the relative risk. And I'm not saying that everyone who teaches introductory statistics should teach relative risk, but I am saying that looking at a ratio of proportions is a pretty reasonable thing to do, and it has a nice interpretation. And in fact, we can go one step further. Like I said, I'm obsessed about this. I'll drag it on for at least one more slide. Does that number look familiar? Hopefully, when you saw the 1.865, you said yes. We just said the difference percentage-wise was 86.5%. That's not a fluke. That's not a coincidence. You can calculate the percentage difference by first calculating the ratio of proportions, subtracting 1 and then multiplying by 100%. So my advice is not that everyone needs to teach relative risk throughout all statistics courses, but I do think it's a good idea to give students lots of practice with percentage difference and percentage change, as it is a tricky concept, especially when you're dealing with percentage change in proportions and percentages themselves. And the other piece of advice I'll offer is that I do think ratio of proportions is at least as important and also easier to interpret than taking a difference in proportion. I'll leave my obsession behind now. Thanks for indulging me for a few minutes there. There's my confession, which I already confessed twice before. My fourth example, and boy, it's going quickly here. My fourth example is oh no, I don't want to, I just lied to you. I'm not done with this example yet. Sorry. I want to say one more thing about the example of the nicotine lozenge to help smokers quit. If we do a hypothesis test here, if we test whether that difference, those two proportions, differ significantly, quote unquote. The Z statistic is 3.6 something. The p-value is very, very, very small. So natural next question is, do the data provide strong evidence that the nicotine lozenge is more effective than the placebo? And the answer is a resounding yes. Test statistics big, the p-value is tiny. It's very, very, very unlikely that such a big difference in the groups could have happened by random chance alone. So sure enough, this study provided very strong evidence that the nicotine lozenge was better than the placebo for helping smokers to quit. And I just gave my students a quiz where they worked through this and drew that conclusion. And I just blogged about it this past week in case anyone happened to read that. But here's the final question I asked on that quiz. Is it reasonable to conclude that most smokers who use a nicotine lozenge will successfully quit? And boy, it's tempting to say yes. Look at that big test statistic. Look at that small p-value. There's very, very, very strong evidence that the nicotine lozenge is more effective than the placebo. That doesn't necessarily mean that most smokers will successfully quit. In fact, look back at the data from this study. It was only 18% who successfully quit. So the odds are still against them. Quitting smoking apparently is a very, very hard thing to do. The nicotine lozenge gives you a much better chance than the placebo, but it still doesn't give you a very good chance of quitting smoking. So better than placebo does not necessarily mean good. And I hope these are good questions to ask students, questions that give them practice applying a procedure and drawing the right conclusion, but also taking a step back and looking at the big picture and seeing where they should be careful not to go in terms of their conclusion. Now let me segue to my fourth and final example here, which is a probability question that I like a lot. One of the reasons I like it a lot is that it brings in other areas of math to be able to tackle and solve this probability question. I like to call this random rendezvous. It's certainly not original to me. I know that Frederick Mosteller's wonderful book, 50 Challenging Problems in Probability, has a variation on this question. And it may well have been around before that also. Anyway, suppose two people agree to meet for lunch at a restaurant. And boy, isn't it nice to think about days when people could actually meet for lunch in a restaurant? I remember those days fondly. Here's the rules. Each person says, I'll wait 15 minutes. They're both busy people. They can't afford to wait all day. And they also are busy enough they don't know exactly when they'll be able to arrive. So their agreement is, first one who gets there will wait 15 minutes. If the other hasn't arrived, they'll take out their lunch and leave and try again later. I guess I'm assuming they aren't communicating by cell phone or anything like that. Let's also assume each person arrives at a random time between noon and 1 o'clock, independently of each other. What do I mean by random time? I mean their arrival time follows a uniform distribution between noon and 1 o'clock. Same distribution for each person, independently of each other. But one thing I like about this problem is it's pretty easy to state. That's the statement. You know what the question is before I tell you. How likely is it that they successfully meet? In other words, what's the probability that they successfully meet? In other words, if they make this arrangement every week for their entire lives, what proportion of days will they end up successfully meeting for lunch? That's the question, that's the problem. We're going to tackle this a couple of different ways. And I often tell my students there are multiple ways to tackle probability problems. There are two major avenues to take. You can take a simulation-based approach or a mathematical-based approach. And we're going to use both here. So let's start by thinking about how we would simulate this random process. I got ahead of myself again, sorry about that. The second question we're going to tackle is if they agree to adjust their waiting time, how long would they have to wait to have a 50% chance of meeting? or even better, a 90% chance of meeting. Let's think about how we would simulate this. And I ask students to brainstorm about the simulation process. You can think of this as coming up with pseudocode. What do we have to do to simulate this random process? Well, we need to simulate the arrival times. We need to generate a large number of arrival times for each person. And then we need to look at the difference between the arrival times for each simulated day. We'll need to determine whether the absolute value of that difference is less than 15 minutes or not. And then we're almost there. Then we just have to count up how many days produced an absolute difference of less than or equal to 15 minutes. And then we're really close. We're virtually there. We just divide that count by the simulated number of days or the number of repetitions in the simulation. If you're teaching a course that involves programming to any extent, you could have students write the code, or you can give them the code, or you can just show them the results like I'm about to show you. The other thing we're going to do is we're going to produce a pretty graph along the way. You ready to see the pretty graph? This is one of my favorite graphs. I think it's very pretty. Let me ask you to guess what it's going to look like before I show it to you. And let me try to clarify, what in the world am I talking about? I'm talking about a scatter plot of person one's arrival time versus person two's arrival time. If you imagine that, it's probably not pretty at all in your head. What's going to make it pretty is let's use different colors for the times when they meet and the times when they don't meet. Let's use green for good, so green when they meet, red for when they don't meet. So imagine that in your head. And the big question is, where's that green patch? Remember the rules here. Their arrival time is anywhere between noon and 1 o'clock. So the entire set of possible arrival times is a 60-minute by 60-minute square. So try to imagine in your mind where in that square do they successfully meet. And I usually say something like the following to my students: what's the ideal circumstance? The ideal is they arrive at the exact same moment. Where's that going to be in this 60 by 60 square? That's going to be on the 45-degree line on the diagonal. But then on either side of that, they've got 15 minutes of leeway when they also meet. So let me show you the pretty graph. There's the pretty graph. This is a simulation of 10,000 days. And you can see green dots are when they successfully meet. Red dots are when they don't successfully meet. The ideal situation is right in the middle of the green swatch there, the 45-degree line. Then we just have to count how many of these dots are green divided by the 10,000 repetitions that were simulated here. And in fact, let me try to, it's going to work. Let me try to go to R and show you. I went too far, I think. I think you can see my RStudio screen there. And I'm not a very good R programmer at all. I'm not a good programmer at all. But I have written a little program that does this. There's the number of repetitions. There's the 2 vectors of random uniform data between 0 and 60, where capital N is the number of repetitions. This program will produce a histogram of the arrival time for each person and a plot, a scatter plot of the pair of their arrival times. So let me run that part of the code. And that's not a pretty graph at all. That's just showing you the 10,000 dots. It's uniformly distributed within this square. The more interesting part comes when we look at the difference in arrival times and the absolute value of the differences. And we can look at those graphs. If I back up, there's the differences. That's a triangular distribution. The absolute value of the differences looks like that. And then we can specify the waiting time, create a logical vector, a Boolean vector of trues and falses for whether the absolute difference is less than the waiting time or not. And then we can sum up that Boolean vector, which will count how many successes there were, and divide by the number of repetitions. Let me run that part of it. And for this simulation of 10,000 repetitions, our approximate probability is 0.4385. Next is how I generated the pretty graph with the greens and reds, depending on whether they successfully met or did not successfully meet. So that's kind of fun, I think, and it produces a pretty graph. And if you're teaching students where coding is part of your learning objectives, I think this is a relatively easy programming assignment. Let me go back to PowerPoint. Now let's calculate the exact probability. How are we going to do that? We need to find the area of that green patch within this 60 by 60 square. How do we do that? We do that by using geometry. I don't even,
Break it up.
Are you seeing the right screen now?
Yeah, I am.
Kind of confused about which screen you're seeing. Let me ask, what's that green patch called? What geometric figure is that?
Rhombus? No, a parallelogram.
Is it a rhombus?
Not quite though.
Parallelogram, I believe that. It's been a long time since I took geometry. There's probably a formula for the area of that region, but I don't remember it. But I do know what the red regions are. The red regions are triangles. And I know the formula for the area of a triangle. And so I advise students to find the area of a triangle. And the two areas of the two triangles are going to be the same. So find one of them and double it. And then subtract from the area of the square to find the area of the green region that we want.
Good idea.
There's how it turns out. Turns out the exact probability of the two people successfully meeting in this situation is 0.4375. A little less than a 50-50 chance that the two people successfully meet. Then what? Then we could say, well, suppose they consider that not good enough. They want to meet at least 50% of the time. They can do that if they increase how long they agree to wait. If they agree to wait more than 15 minutes, they can make this probability bigger. So let's see how long they have to wait to make that probability bigger. How do we figure that out? Well, this time we need algebra. We need to express the probability of successfully meeting as a function of the number of minutes that they agree to wait. And I'll spare you all the details, but you can imagine it. We just use the area of a triangle again, except now instead of the triangle having a width and height of 45 minutes, the width and height will be 60 minus the waiting time. So 60 minus L. That's the same for the height and the width, so that's why it's squared. Where did the 1/2 go? Well, we've got two such triangles, so the 2 times 1/2 took care of that. So there's the probability of successfully meeting as a function of the number of minutes that they agree to wait. You can set that to be greater than or equal to 0.5 and solve for L. You'll find they need to wait 17.5 minutes roughly. If they want to have a 90% chance of meeting, they need to wait almost more than 41 minutes. As I sort of mentioned when I started, I chose these examples in part because they have some connections with other areas of mathematics that might be fun to work in. And frankly, I didn't know if all of you teach a statistics course or you're just interested in teaching statistics as it relates to other math courses you teach.
I teach stats.
So maybe there are some ideas here for incorporating some probability and statistics into other math courses. If you are teaching a statistics course, you might follow up by saying, well, what if the arrival times followed normal distributions rather than uniform distributions? Can we tackle that situation? Sure, we can. We can tackle it both with simulation and with math. We go back to the simulation. The only thing we have to change in the R code is the statements about R uniform. We change R unif to R norm, and then input the mean and standard deviation that you want to use, you're good to go. And I've got that in another file here. So let me run the whole thing. I think I'm setting both means to be 30 minutes after the hour, both standard deviations to be 10 minutes after the hour. And that's another pretty picture, I would say. So now we've got an ellipse there. It's concentrated around the point 30, because both of their means were assumed to be 30 minutes after the hour. And you can see, I think, that the green band is more plentiful now than it was before. So the approximate probability that they successfully meet is up to about 71%. And you can follow up with normal calculations to see what the normal distribution says for that probability. Why do we need the normal distribution? Because we're dealing with the difference of two normal distributions, which will itself have a normal distribution. That works out to be another normal distribution calculation. So as Chris mentioned at the top, I wanted to mention that I've spent the last year and a half now writing a weekly blog called Ask Good Questions. I try to provide ideas, examples, activities, assessments, and advice for teaching introductory statistics. I have 3 goals for every post, and I'm sure I don't achieve them all with every post. Hopefully I achieve one or the other once in a while. But my goal is for every post to be practical, to show you something you can use with your own students. My goal is you read it on Monday and you think, I could try this with my students on Tuesday or Wednesday or whenever. I also try to be thought-provoking and give you food for thought and give you things to discuss with your peers and to have an internal dialogue with yourself. And it's very non-academic writing. I try for a very conversational tone. And I throw in attempts at fun and humor from time to time as well. There's been 1 post/essay per week for a year and a half now. They're published on Monday mornings. I try to write a full essay for each week. I think I mostly succeeded in the first year, because the first year I did this, I was on leave, and my leave project was to write this blog. So frankly, I spent 15, 20 hours a week at least working on these blog posts. I put an awful lot of time and thought into it. But since September, I've been back teaching full time, and I don't have 15 to 20 hours a week. I'm lucky to find, I try to find 5 or 6 hours a week now to write a blog post. So they probably aren't as good as they used to be, but I'm still producing something every Monday. During the summer, I asked lots of people to write guest blog posts, including Chris and Roxy. And I've had a few guest blog posts now and then since then. So please check it out if you care to. It's askgoodquestions.blog. I want to conclude with an old joke I'll let you decide whether it's a good joke or not, but then we'll get to my moral of the joke. The old joke is about a talking dog. A man has a talking dog. He thinks this will be the greatest entertainment act ever, himself and his talking dog. So he goes to a talent agent and says, I've got this talking dog. Let me show you. It's a great act. You'll want to represent me. And the agent is already skeptical and says, all right, let me hear your talking dog. So the guy says to his dog, what's on top of a house? The dog says, roof, roof. The agent's ready to kick him out of his office. The guy says, let me ask another question. How does sandpaper feel? And the dog says, rough, rough. Now the agent gets up out of his chair. He's going to physically remove him from his office. The guy says, one more chance, one more chance. I've got another question. Who is the greatest baseball player of all time? And the dog says, Ruth, Ruth. And the guy kicks him out of his office, and the dog too. And then out in the hallway, they're crestfallen. The dog looks up at the man with the with a sorry, sad, perplexed, crestfallen look on his face. And the dog says, DiMaggio? Maybe it's not a good joke. I've always liked it. What's the point? The point is, what was the person's mistake? I would argue his mistake was that he did not follow the advice to ask good questions. He had a dog who was capable of doing great things, but he didn't ask questions that elicited a great response from the dog. And I think that's what we need to do with our students. We can help our students to learn and grow and do great things if we ask good questions. Thanks very much for coming and listening to me. I did want to make a plug, like Chris already did, for the US Conference on Teaching Statistics. The theme this year is expanding opportunities. It's going to be held virtually this year. To be honest, I'm sad about it being virtual. I love getting together in person with people at conferences in general, and certainly at US Cons. But I'm happy in that I hope that lots more people will be able to attend since it's being held virtually. Amy's one of the program committee members. I think we're going to have a very good program. I think we'll have lots of sessions that are relevant and appropriate for teachers at lots of different levels. I see a typo in my address for the Ask Good Questions blog. It really is Ask Good Questions, not Ask Good Questions. There's my email address if you want to talk to me afterwards. We've got 20 some minutes left to do some Q&A now. Let me stop sharing and give you a chance to say something.
So Alan, thank you so much. I thought what we could do is you could either put your question in the chat or just speak up. I think it'd be really nice to just interact some. There was one question that was in the chat while you were talking, and this is when you were talking about your smoking example. Do you by chance, are you aware of any good data that looks at vaping versus cigarette smoking?
Yeah, I've used an example in class that looks at vaping. If you want to email me, I'll email back with the reference. I can probably find it fairly quickly. To be honest, I don't use that in class anymore just because I don't know, vaping's kind of controversial, and the study that I saw showed that vaping was effective for helping smokers to quit. But whether college age students and high school age students should be, I don't know, thinking positively about vaping is another question. So I don't know if it's such a good example to use with students after all.
Well, I'm going to open it up for you to ask Alan questions.
If anyone wants to take the opposite viewpoint and argue in favor of asking bad questions, I'm happy to listen to the opposing viewpoint.
So bad questions are easier to grade.
So Alan, I'll ask a question. I'll put you on the spot. Of all the blog postings that you wrote for your Ask Good Questions, do you have a favorite?
I guess I would say no. If you want to know a few, if you want to give it 15 minutes and look over a few, I would start with the first one, which is just called 10 questions about this blog or something like that. I like the one is called A Pervasive Pet Peeve, which is about the percentage changes and the relative risk in that. I like that one. The one I wrote for number 52 at the end of my year leave, I hope that's a good one. It's called Top 13 Topics or something like that. One that I got a lot of feedback on, positive feedback on, was one I wrote when I first started teaching again in the fall. And I was teaching entirely online. And I missed out last March when most teachers in the world had to move at a moment's notice to teaching online. Well, anyway, I wrote a post called My First Video, which is about how difficult I found it to produce my first video. And I was aiming for humor, and some people were nice enough to tell me I succeeded. So you might look over my first video post.
Alan, it's David Spawn. How you doing?
Hey, David.
So unfortunately, I'm giving the American math competition at the same time. I'm doing like 5 things right now, so I missed a lot of what you were doing as things were going on. But something so I'm going to tell my question first, but then I'll give a context. So my question is, what would you want if a student was not taking AP stats, and right now I'm teaching a semester stats course to seniors, okay? And so they've had algebra 2, they're not taking AP stats. And so I got brave enough this year. As I get older, I've gotten braver. I've taught the course in the past, basically being Stats 101 light, and just kind of following a traditional, first year stats course, and just doing as much as I can, and I guess asking bad questions, just following a textbook. And this semester, I just said the heck with it. The textbook has not come out, and I'm actually right now I'm 3 weeks into something I'm called experiences in statistics, and basically, for example, they did the switch or stay, Monty Hall dilemma, and look at simulations, look at probabilities, and so forth, and we're doing things like that. But I have no idea how to assess them doing this, but they're having a great time, and we're hitting things, so my issue is I don't want it to just be fun and games. I want to be a development. As a matter of fact, every time we do an activity, we have to chart out, okay, what did we learn statistically? Okay, and we have to have at least 3 or 4 things. But I don't know how where's the unit test? I'm not, I don't have a test on normal curve and so forth. And I guess what my inquiry for higher ed folks is, what kind of kid do you want showing up for Stats 101? What would you want us to do at the high school level as we get a chance to teach them maybe a senior level course?
There's a lot there. I think your course sounds great. And I don't know if this is answering your question exactly, but I think the specific content matters a lot less than the experience. The giving students experience analyzing data and thinking about data and drawing conclusions from data is a lot more important than checking off the list of specific topics that you've covered. So, I mean, in terms of coming into Stat 101, I guess I'm thinking more about students who take your course and then never take another statistics course. So that's what I want them to see. I want them to see real data, exploring data, finding insights in data, drawing conclusions from data. Some ideas probably about confounding and cautions about the kind of conclusions you can draw, depending on how the data were collected. But everything I'm saying is stuff that I teach in Stat 101, so it's not necessarily stuff I want students to know before they get to Stat 101. So I think your question about what do I want them to know before they get to Stat 101 is somewhat stumping me. I will say percentage change.
And it's almost an attitude thing. I think having them have had good experiences with statistics prior to coming into 101 sets the stage for them to be really successful and engaged in 101. So providing the kind of experiences you're providing, I think, is a good thing. As long as they're having a good experience. It's almost mindset, I guess.
And I really like what you said, David, about at the end of every activity, you pause and reflect on what they were supposed to have learned from it. I think that's great, and I think that's crucial. Where else students might perceive it as fun and games and not realize they're learning substantive things along the way.
Alan, there's a couple of good questions in the blog, 2 or 3 questions. One is your thoughts on multivariate thinking, especially multivariable regression. Do you have some good resources for that? Do you talk about it in your blog? Also, what do you think students should know when they leave high school? And then what do you see as the relationship between statistics and data science? So those are 3 good questions for you.
Yeah, very good questions. All very easy to answer in 10 seconds or less.
Right.
Let me start with the multivariable thinking. I think that's a really important thing and a great thing to be teaching. I've talked about that a little bit in some blog posts, but not a whole lot. I don't think I've talked about multiple regression per se, but I've got a couple that deal with multivariable thinking. I had a series broken up over several months called Statistics of Illumination. That goes back to the famous quote that most people use statistics as a drunk uses a lamppost, more for support than for illumination. Sometimes I give a talk, sometimes when I'm asked to visit high schools, I give a talk called Statistics of Illumination, where I try to argue that statistics can be illuminating on important issues. And I also try to show in that talk that you don't need fancy math to be able to do statistics and draw insights from data. That's a 4-part series in the blog. 2 of the parts deal with multivariable thinking. I'm trying to remember which ones. I think the very first one, which deals with the famous data from the Berkeley graduate admissions process. It's an example of Simpson's paradox, if you know that term. But Simpson's paradox is an example of multivariable thinking, usually with categorical variables. And I've got another, I think it was the 4th in the Statistics of Illumination series that deals with a somewhat well-known data set that looks at lung capacity and smoking. And the surprising result is that in this data set, smokers tend to have larger lung capacities than non-smokers, which seems really weird and backwards until I let you in on the little secret, which is that the data was selected on kids aged 8 to 19. And so, of course, it's the older kids who are the smokers. And of course, older kids have bigger lungs than younger kids. So that's another fairly simple introduction to multivariable thinking. Yeah, I think multivariable thinking is an important skill and a great thing to help students learn. And I think I have 2 blog posts I mentioned that deal with it directly. And I've heard Roxy give talks on this, and she's got lots of great examples that you may have heard as well. What should students know when they leave high school? Let me point to one of my blog posts again, number 52, the one I wrote at the end of my year leave, that tries to summarize what I think are the most important things to learn. And what's in there are things like the idea of confounding and the difference between random sampling and random assignment, what the goal is for random sampling and random assignment, what kind of conclusions you can draw based on random sampling and random assignment. Just the basic idea of variability is an important one. Basic idea of association between variables. The very, very basic idea of observational units and variables. So things like that, I would say. I would say the basic idea of statistical inference, which means the idea that sample results vary, and you can use that variation to decide whether there's strong evidence of a real effect there, a real signal behind the noise, if you will. And I'm, as you may know, a big proponent of introducing ideas of statistical inference through simulation and not through mathematics and normal distributions and formulas. There are a few ideas off the top of my head. I would refer you to post number 52 for more there. The question about data science is a great question, and I think about it a lot, and I don't have any special insights there. I think there's, you folks probably know better than I do, but I've read that there's a real push to put an emphasis on data fluency in the high school math curriculum. I listened to the podcast with Stephen Levitt that many mathematics educators appeared on, and it sounds great to me to put data fluency as a focus in high school mathematics curriculum. It's not completely clear to me what data fluency means or how data science is different than statistics, but I'm not sure that's all that important to decide those things. But I guess I've come in the last 5 years to believe that there are aspects to data science that go beyond statistics. I think I was probably reluctant to believe that. I'd probably like to think that data science was just a rebranding of statistics and a more fashionable, popular name for statistics. I've come to believe there is more to it than that. Frankly, I lack a lot of data science skills. I wish I had the skills to go online and scrape data from the web. I wish I was a really good programmer and can organize the data really efficiently and then produce the relevant visualizations and draw insights from the data. And I'm good at some parts of that, but I'm really not good at all at other parts of that. I think if we can teach students that entire process of gathering data and organizing the data and wrangling with the data, as is a term sometimes used by data scientists, I think that's all a good thing, as long as we're still helping them learn basic statistical principles and concepts as well. Of course, I would say that part as a statistician, somebody who's a data scientist or computer scientist might not care as much or think as much about the statistics part. That's a rambling answer to that question.
So Alan, here's a question. What student responses do good questions elicit?
Yeah, very good question. I haven't yet written a post. Somebody asked me after my first or second post to write a post that would describe what makes a question good. And I haven't done that yet. And partly it's because I think it's a hard question and I haven't sat down and thought hard about it. Partly that's sort of my teaching philosophy, is to work from examples and questions and not so much from the overarching principles and theory. But I think part of what makes a question good is, needless to say, making students think. So I think a good student response to a good question indicates that they had to think. They had to think something through or make connections between ideas. I think helping students make connections between ideas is an important part of thinking and learning, which is part of why I like the random rendezvous activity so much. Making connections between probability and coding, between probability and geometry, between probability and algebra. I think the extent to which we can encourage students to ask their own questions is a wonderful thing and a great sign of success. Those are a couple of thoughts. These are such good questions. I'd have to think a lot harder about them to have better answers.
Here's one. Do you use logistic regression for anything specific?
It's pretty rare that I teach a course that uses logistic regression. So myself, no. But I do think logistic regression is an important tool and a good one to have in a toolkit. I think it's a pretty rare Stat 101 course that introduces logistic regression, but it's fairly common in a second course and a Stat 102 course. Boy, I haven't taught logistic regression myself in a long time.
Here's a question. How do good questions in statistics courses intersect with teaching statistics to social justice?
Yeah, great question. I think there's a lot of great opportunities there to expand students' horizons and make them aware of inequities in the world by giving them examples that use data to illustrate inequities and injustices in the world. And there's a lot of people do a lot of work in that area, and I think that's great. I would also add, I've given several talks in the last couple of years where I argue for using data sets that introduce students to ways in which the world has demonstrably and measurably gotten better in many ways. So I show my students data on things like the percentage of the world living in extreme poverty. And they're pretty shocked to realize that percentage has been falling drastically for the past several decades. I agree wholeheartedly with the idea of using data sets to introduce students to statistical ideas and also to injustices and inequities. But I would also add, we can use data sets to introduce students to ways in which the world's gotten better in demonstrable ways as well. If you go to my blog site, there's a link for presentations. Like I say, I've given several presentations about human progress. Over the past couple of years, you can download some of my slides from those presentations if you're interested in that.
Are there more questions? No more questions for Alan? Well, Alan, thank you so much.
Thanks for the invitation. Thanks everyone for coming. It's awfully nice of you to give up an hour of your time in this busy world. So thank you very much. Nice to see some familiar faces. Hi, Jerry.
This is a great group that comes for the chats, and we really appreciate you joining us today.
My pleasure. Thank you all. Take care.
So everyone, just wanted to say our next chat is scheduled for March the 4th. And we plan on having Holly Lynn Lee from NC State and her team. They're going to join us and give us a presentation on using CODAP, which is open source software. So we're really looking forward to that. And we'll be sending out more information on that as time gets closer. And of course, the sign up. So thank you again, everyone. I think we're going to finish on time. Thank you again, Alan.
Thanks,
Good
Ellen.
thing. Take care. Bye, everyone.
Bye, everyone.